All right, so I have a question for you right off the bat. A sort of refresher from last time. This is posed in a very interesting way. So, high-speed train is traveling at a constant velocity, a straight line from capital city to Shelbyville. According to an observer, so that means, according to an observer at rest on the ground, the clocks on the railroad stations in both cities strike noon at the same time. A person on the ground says these are simultaneous events. And there's a passenger on the train, and they just left Capital City. They're on their way to Shelbyville. That means they're heading away from Capital City and heading toward Shelbyville. And what would they say is going on with the time in Shelbyville? Letter in the chat. Let me know what you think. So the question you're asking yourself here is, what event do you believe took place? The events being strike and noon. C's. Looks good. When you are approaching the event, the way the time is going to flow here, the clock at Shelbyville strikes first, then the capital city one strikes. So that means by the time the capital city is gone, Shelbyville is already past noon. Okay, great. Now, one of the things that we're going to be doing here today is we're going to start to put some numbers behind these things. Okay, how to count? When we say afternoon, how much afternoon? Based on the speed of the train, we could determine how far afternoon that clock is going to be. So the principle here that you'd want to remember is when you're approaching something, the event is going to appear to happen early. If they're simultaneous in the ground frame, the event that you're approaching is going to appear to happen earlier than the one on the other side of you when you're moving away from it. All right, so first thing we're going to tackle now, because what we've been talking about here in the last lecture is the concept of time flowing differently. And so what we want to do is we want to know, well, how much, in what way is time flowing differently? And the way we're going to go about trying to establish this is with something called a light clock. And the idea with the light clock is you have a detector. Now, in the picture here, I don't really like the way they did the picture. Just imagine that the light source and the detector were basically kind of the same thing. It could shoot light out, and it can also detect light. And the distance, and if there happens to be a distance between them, it's negligible. It's just basically nothing. The idea here is that you could shoot a light beam up, hit a mirror, have it come back down, and you can time that. And if you release light at regular pulses, it's like a clock, right? Just at equal intervals, a light source is emitted and then detected, emitted, detected, emitted, detected. Okay, so every time a beam goes up, hits, comes back down, we get a little tick on the clock here. Okay, it doesn't have to be seconds; it just needs to be even intervals of time. Where ultimately, when we say if you really think deeply about that, what do we mean by equal intervals of time? I mean, anytime we keep track of time, it's because there is an event that repeatedly takes place, and that repeated event that takes place indicates a passage of something, right? Passage. That's the concept of time that we're having here. So in this particular case here, our clock is somehow, it's the concept of distance is incorporated into time here because the beam has to travel a distance. And so the speed of light is kind of inherently built into this concept of time, at least in the way we're setting up the time clock here. It doesn't always have to be that way. I mean, the way we do time now is by measuring the oscillations of a cesium atom. And those are, periodic enough events that they're very precise. Okay. Anyway, I'm not going to get into that right now. All right, so what we're going to do with this light clock here is we're going to let it run through ticks, and we're going to have two different observers view this clock. The clock is going to be kept in a move-in reference frame. So the clock will be moving, say, to the right at a velocity v. So there is an S prime frame, which represents the rest frame of the clock, and then we're going to have an observer externally watching the clock move. And what we want to do, I don't know if I'm choppy or what, but my video is pretty choppy. Hopefully I'm coming through okay. Anyway, what we're going to do is we're going to have a person in the S frame make observations. So we have events here, right? The event is each observer. Okay. Each observer is going to watch a tick of the clock. We want to see how time flows for those two people. Now, for, oops. Okay, now in the S prime frame, it's pretty easy to express what's happening here. A light ray goes up, hits a mirror, comes back down. So what we can say here is, rate times time equals distance, right? So that means what we're going to say here is the speed at which the light pulse moves, we'll call that delta C, C, times a delta T. And I'm going to put a prime there to indicate that this is the rate at which the time is flowing in the S frame, is equal to 2h. Okay, that's an h there, 2h. 2h because the light beam goes up and it comes back down. And so we can specify here that T prime is 2h over C. So every tick that happens on the clock in this frame is dictated by the speed of light going up and down, up and down. So 2h over C represents that period of time. What about the S frame? In the S frame, this is what we're looking at here. So the mirror, the detection, everything is moving to the right at a speed v. So what happens is the path length that the beam of light takes is longer, because as you can see here, as the observer in the S frame sees, the beam doesn't just go up, it goes diagonally. Hits the mirror, comes diagonally down, hits the detector, because everything is moving to the right. But the speed of light is still the speed of light. If we were doing things in Galileo's time, we would have to up the speed of C here, because we would say that the speed of light is a component going upward, and then the velocity of the train going this way. But speed of light is speed of light. So that's not... So if we look at this, we have like a triangle here, basically. Okay? And the way that you can view this, they put a 1/2 C delta T here, because the idea is that the distance that they're describing here is the distance from the emission to the mirror and to the detector. So the distance traveled will be C times delta T, and therefore this distance here is just 1/2 that. Okay, the height of this triangle is h, and the base is how much the detector has moved to the right, which is v delta t. But again, we put a 1/2 here because this is referring to, the t delta, the v delta t is referring to the whole distance here. Okay, so we put halves here just because we're looking at just this half of the path here. So Pythagorean Theorem tells us that h squared plus 1/2 v delta t squared equals 1/2 c delta t squared. That's how we would relate those concepts there. If we solve for delta t, okay, so you can square everything, multiply this by a 2, or a 4 really, right? Square everything, multiply everything by a 4. move the v squared over to the other side. So it's a bit of algebra, not a lot of algebra, but it's a bit of algebra, but you can rearrange things. You're solving for delta t, and if you do that, you end up with the equation that's down here. Delta t equals 2h over c divided by this radical term here. Now the radical term comes from, there's a c squared here, there's a v squared here, you move the v squared over here, and then you factor out a c squared, and you end up with the 1 v squared over c squared here. Now the 2h over c, we just said what that was in a couple slides ago. That is the rate at which time is flowing in the s prime frame. And so now we have it. We call this effect time dilation. And it's the idea that time flows differently in different reference frames based on the relative velocity of those frames. So in this equation here, we are relating the rate at which time flows in a stationary frame to the rate at which time flows in a moving frame. And the only thing you need to put in here is what the speed of that frame is. Now, if you look at this, well, let's jump ahead here. Okay, so this entire expression here, 1 divided by radical 1 minus v squared over c squared, that is what we call gamma. It's also called the Lorenz factor. And it's the proportionality between the S prime frame and the prime frame. So one thing I forgot I did here, and I have to apologize for, is that I kind of blended together slides from two different presentations, and in one they use v for velocity, and in some they use u for velocity. So sorry for the mix-up there, but u and v are the exact same things. And the notation here, t naught, that's the same as t prime. That's the same as t prime. So anyway, sorry to mix up notation there. All right, so this is what the Lorenz factor is here. Now, if you look at mathematically what this is here, u squared divided by c squared. Okay, that is a number that is less than 1. Now, 1 minus that number is still a number less than 1. When you take the square root of it, it becomes smaller. And then when you take 1 divided by a small number, you get a larger number. The Lorenz factor is greater than 1. So that's one thing you will need to remember here. Is just mathematically speaking, this expression is always larger than 1. Okay? That means when you go back to the time dilation equation here, okay, the delta t naught, the rate at which time flows in the S prime frame, is always shorter than it is in a frame that observes the motion. Okay, gamma is always larger than 1, so this time interval here in the S frame is always larger. We have a name for delta t naught, or delta t prime, the S prime frame's rate of flow. It's called the proper time. Proper time is a length of time between events. It's always the shortest amount of time between events. The shortest amount of time between events. Now, okay. Okay, I'll say that in a minute here. All right, anyway, so yeah. So in terms of that light clock there, in the moving frame, so if a person's in that train observing the clock, what they would call the intervals of time, that by which things go up and down, the arrows go up and down, they would express that with a smaller number than somebody who is standing on the side at rest, not at rest, but watching the train go by. They would speak of a larger time interval here, and this is what relates the two. This relates to. Notice that these are delta t's. They're not t. We're not talking about when a particular event occurs necessarily. We're talking about the time interval between events. Okay, so we're talking about flow of time. Flow of time. Okay, great. Now, this gamma quantity here has a very interesting relationship. So with speed, as you start to up your speed, this quantity is not very large to begin with. When you even get to half the speed of light is let's check it out. 1 minus at half the speed of light, the gamma is 1.15. That means the frame experienced time intervals 15% larger than the S prime frame. If we go down to say 10% the speed of light, at 10% the speed of light, that is really small, actually. 1.005. Okay, that is 0.5% difference. And 10% the speed of light is pretty darn fast. So what this is saying is this: relativistic effects are really small. Even at 10% the speed of light, which is very fast, the relativistic corrections you need to make are less than 1%. See here, there's something really dramatic starts to happen. When you start getting up really close to the speed of light, this becomes asymptotic here. And this thing just shoots up. Okay, this thing can never, as the speeds go up and up and up, you'll never reach the speed of light, but the value of this gamma factor gets extremely large. If you have like 0.999% the speed of light, 0.999% the speed of light, what's that gamma factor? 22 at 0.999% the speed. 0.999 the speed of light, the gamma factor is around a little over 22. That's a big deal, but you gotta go awfully fast for that. So my point here is that relativistic effects are pretty minor until you get to a particular speed, and then they really start to fly. Up here. All right, now, one of the things that's really challenging about this concept here is being able to understand what the proper time is. If we have a situation where we have two reference frames and we have events happening and these different observers are looking at them, how do we know which one's the proper time here? And the easiest way to know that is the proper time is when two different events occur at the same location in the reference frame. Same location in the reference frame. For example, say somebody's in a train and they're passing by, two locations, for example. Now, in the S frame, we see a train go by and we see event 1, you pass this marker here, and event 2 happens further down the way when it gets to the second marker. Those are different locations. And so those are going to be affected by time dilation, and you look at the speed to figure out what the time dilation effect is. But what's going on in the train's reference frame? The train's reference frame, there's a marker right next to you that represents that first event. Now in your reference frame, what's happening? Your reference frame, the environment is moving, right? The train's stationary in your reference frame. You're at rest relative to the reference frame, the train. And the markers are coming towards you. So there's a marker right here, boom, and then time is going by and the environment is passing by you, and the second marker now gets to you, bam, now it's at you. Now it's right at your location. Now, so those two events took place at the same location in that reference frame. Okay, so this statement up here is something we got to be very mindful of when we look at situations. Okay. One of these reference frames, usually one of the references, it's possible you have two reference frames that are both not part of the moving frame. That's possible. Then there would be different rates at which time flow. Okay, fine. But identifying the proper time is key here. Okay, same position for the events. In that frame, though. In that frame. Okay. All right. Is that good? That's good. That's good. It is good. Let's keep pushing on here. All right. Now, question for you here. Samir, who is standing at rest on the ground, starts a stopwatch at the instant that Maria passes by him in her spaceship. Samir is S frame. Maria is S prime frame. At the same instant, Maria starts her stopwatch. At the same instant, Maria starts her stopwatch. Okay, so that's event number 1. Event number 1, start the stopwatch. As measured in Samira's frame of reference, what is the readings on Maria's stopwatch? So say somehow you could see her stopwatch and she's flying away. And what's the reading going to be on Maria's stopwatch at the instant that Samir says 10 seconds have passed? Okay, so a bunch of you said A. Okay, we got one B in here. It is B. It is B. It's not the same. Maria is moving relative to Samir here. Maria has the proper time. So what are the two events? The two events are when the stopwatch starts and when the stopwatch reaches, well, for Samir, when it reaches 10 seconds. Okay. Now, so they both hit their stopwatches and they stop them. Now, Samir, these two events, watching Maria's stopwatch, takes place at different locations. Okay, when the stopwatches start, Maria's right next to him. Okay, when the stopwatches are clicked to stop, way down over here. So those are two different locations. What does Maria say? She says, I hit a stopwatch here, and I'm just standing here. I'm not doing anything. And then I hit stopwatch again. Okay, and she sees Samir's flying that way. Okay, so she's got the proper time because the two events that she's describing are at the same location. Samir says, well, the two events are, one was right next to me and then the stopwatch is way down there now. Okay, because we're looking at Maria's stopwatch here. We're talking about what's going on with her stopwatch there. Less than 10 seconds. Okay, so because Maria has the proper time, we don't know what the time actually is, but we know it's less than 10. That's the idea here. Okay. Yeah, she's in the spaceship and he is standing. Right. So now the events are, what's going on with Maria's stopwatch. That's the idea. What's going on with Maria's stopwatch. All right. So we see time dilation in a lot of ways, actually. One of the first ways it was recorded and measured was with relativistic particles. So, we see this in particle accelerators. We also see this when cosmic rays hit our upper atmosphere and they dissociate. Muon is a very common subatomic particle. And it's something that's created in high energy, when a high energy gamma ray hits our atmosphere and it cascades down to lesser energies or particles. We see that. Now, our theories for how muons work is that in the reference frame of the muon, we calculate what its half-life is, and it's around 1.5 microseconds. Now, in our reference, that's the proper time. That's the proper time. When the muon says, when I'm created to when I die, 1.5 seconds passes on average. That's the half-life. Well, it's not an average, but you know what I mean. Okay, it's a half-life. But we observe the muons traveling for a much longer period of time. And it's consistent with their speed and how long we actually measure them to go. They usually can last a much longer period of time, actually. And we see this, again, particle accelerators, very common in particle accelerators, or just observing atmospheric events. So this is a strange thing but something we've confirmed. We actually do these in a lot of different ways. For example, they bring clocks up to the space station, synchronized clocks. They measure time dilation rates. GPS satellites. In fact, I remember when I was in undergrad at Cal Poly Pomona, we had a person come in to give a talk on GPS satellites, and I had just taken relativity, and I remember asking the person giving the talk, because it was all about triangulation and orbits and things like that, and I remember telling the guy, like, what's up, you guys got like time dilation corrections? And he's like, hell yeah, we do. He didn't say hell yeah, we do, but he's like, yeah, we do. He's like, the signals that get sent up and come back, the satellites are moving reference frames. So time flows differently, and in fact, it's a significant factor because, the global position satellites, they're pretty accurate. I don't know what the accuracy is these days, but I mean, they can typically track. I mean, last time I remember, they could track things within a meter, and so that requires really precise measurements of time here. And so I remember the guy went on and on and on and on, and I was like, kind of regret asking this question. You kind of give me a rant now, but I was a kid, whatever. Okay. Oh well, I've heard that actually. I've heard that about at least for the resolution of images, they definitely exceed what is available to a lot of the scientific community. I remember that also too. I don't know why I remember this, but like a lot of the vast majority of computing power got its start from military applications. I remember these jets from the 60s. They could have run Super Nintendo games. Apparently, that's what I had read. They were 16-bit systems. Dang, what? Okay, wow. Okay, so yeah, these are important things, and the precision is important. I mean, I'm talking about these corrections not appearing very much, but yeah, if you need precision like this, I can imagine. Yeah. All right, good stuff. Good stuff. All right, let's do some examples. Let's get into it. All right. Am I screen sharing this? I am. All right. Am I screen sharing? Yes. Okay. So, ooh. What? I got things out of order here? Hold on, sorry. I got things out of order. Is that true? Sorry, give me a minute here. I got my notes out of order here. Okay, I guess I gotta reorganize this stuff, it looks like. So what's the first question here? Saturn as measured. Okay, I guess this is one here. All right, so let me zoom in because this is a little hard to see here. Okay, so boy, I'm all confused here with my notes. All right, anyway, Saturn is 1.43 times 10 to the 12 meters from the sun. A rocket travels along a line from the sun to Saturn at a constant speed of 0.9 relative to the solar system. How long does the journey take as measured by an experimenter on Earth, as measured by an astronaut on the rocket? Okay, so we got... So when you do these problems, you want to make sure you specify what the S frame is, what the S prime frame is, what their relative velocities are, and what events are taking place. So the pictures we have in the middle here correspond to the S frame, which is the solar system, meaning somebody on Earth watching things. And we're watching this rocket start at the sun, and moves with a particular velocity, which is 90% the speed of light, then it reaches Saturn. Event 1 is the rocket at the sun. Event 2 is the rocket at Saturn. Now, in the S prime frame, for the people who are in the rocket, what do they see? They see the sun right next to them, and then it flies to the left. Saturn starts to approach them. And then when event 2 happens, Saturn has passed them. So in the S prime frame, the events are taking place at the same location. Okay, remember, this rocket establishes a coordinate system that's centered on the rocket, and the sun and Saturn are moving. So in their established reference frame, they are measuring these two events to occur at the same location because Saturn is approaching them. So their spaceship is the proper time. So what we can do here is we can go to the observer on the Earth and say, okay, well, what's the distance between the sun and Saturn? Okay. And how fast is that spaceship moving? And it's just a simple rate times time equals distance problem. We got our 1.43 times 10 to the 12 divided by 90% speed of light. And we get 5,300 seconds. That's how long it should take to get to Saturn. Okay. Now, since event 2 is the proper time, we can take this time here and we can divide it by gamma. Remember, gamma is bigger than 1, so that means you're going to be dividing this number by gamma here. What is gamma in this context here? Well, I didn't work it out here, but let's see, 1 minus 0.9 squared, take the square root of that, and flip it. It's 2.29. That's what gamma is here. So the amount of time goes down by a factor of 2.29. So the people in the spaceship, they are reporting that it only took 2,310 seconds to reach Saturn. That's it. We're going to revisit this problem a little bit later today in the lecture. Because there's something else going on here, actually. Because you can ask yourself this, say, well, okay, I mean, I get it that the time is different, but it may seem a little uncomfortable still because, you know, these things are still moving at that speed, right? Well, there is something else going on here. There is something else kind of going on here that we can take note of, and we'll get to that when we get to it. Today at some point. I don't know when that's going to be, but let's go back to the lecture. Where are we? We've got example 2 here, and that's Mavis and Stanley. So we've got to find that one. Did I just not do this problem? Did I just leave that out? I don't know what I did. All right, anyway, let's get to this next problem here. All right, so Mavis boards a spaceship, then zips past Stanley on Earth at a speed of 0.6 c. All right. So Stanley looks like it's S frame. Mavis is moving. She's S prime frame. Short time later, Stanley measures that Mavis has traveled a certain distance beyond him and passes a space station. What? A short time later, Stanley measures that Mavis... Okay. I can't grammar, apparently. Short time later, Stanley measures that Mavis has traveled 9 times 10 to the 7 meters beyond him and is passing a space station. Oh, brother. What does Stanley's timer read as she passes a space station? What does Mavis' time read? All right, let's tackle that one first. First of all, we got our speed here. So let's just go ahead and get gamma right off the bat here. 1.25. 0.6 c is going to turn out to be 0.125 in gamma. We want to make sure we measure everything appropriately here. So Stanley is S frame, Mavis is S prime frame. And so Stanley's going to see, right, the distance over time. That's how much time is going to pass. So the distance is 9 times 10 to the 7, and the speed at which Mavis travels is 0.6 c, and that's going to take half second. Half second, just flying by. Mavis is in the moving frame, and that she experiences proper time here because the two events that took place are where Stanley and Mavis are together, and then later Mavis passes a space station. So the two events are they're together. The second event is Mavis at the space station. Now, Mavis is like Saturn in this in this example here. She's at rest in her reference frame, and the spaceship moves towards her. So she experiences the proper time. We divide our time by our gamma factor, and we get 0.4 seconds. Slight difference in time. Now, Stanley starts to blink just as Mavis flies past him. And Mavis measures that the blink takes 0.4 seconds from beginning to end. According to Stanley, what is the duration of his blink? We flipped things around here. Again, what are the events? The events are start to blink, finish blink. So these events are measured by Mavis, and these events are measured by Stanley. And the question you have to ask yourself is, in which reference frame do these two events take place at the same location? And that would be the S frame. That's in Stanley's frame. So Stanley is experiencing the proper time for the blink. Mavis sees a longer blink. Okay? She's seeing Stanley move, right? So we take our 0.4 seconds and we divide that by the gamma factor, 1.25, and we get 0.32 seconds. Okay, this is a great problem because it really emphasizes being very clear about, specifying everything. What is S frame? What is S prime frame? What's moving? Who has the proper times? You look at the events that take place. What's event 1? What's event 2? That's the time interval we're dealing with here. Okay, in which reference frame are these two events taking place at the same location? For part A, Mavis has the proper time. For part B, Stanley has the proper time. Okay, this is a really great question. Really, really, really great question, actually. Do you have any questions about this example? Anything unclear about this? All right. So, let's do another problem. And then, let's do another problem and another question, and then we'll move on. The math is definitely not a challenge. Well, actually, I'm lying to you. The math is a little bit of a challenge, actually. In fact, I'll be honest with you, some of the math in this chapter you can't do with a calculator. Straight up, you just cannot do with a calculator. So that's fun. All right. I got things mixed up here. I'm at the end of class, I'll show you a trick that allows you to use your calculator for problems. Sorry. That may seem crazy, right? But yeah. Some of our numbers here are so extreme that the calculator can't do it. Okay, and for those who are, for those a little computer savvy, it's past the floating point. It's past float. So what's float again? Float.
The 10 to the 39.
Oh, I'm wrong about that then. Float.
No, I don't know. I might have just guessed.
Float. Okay.
Oh, for like C++, it's around like 38.
I can't. I can't remember now, but anyway, it's the way that most calculators work. It's beyond the defined variable limits. Put it that way. All right. Anyway, so this is sorry I mixed this stuff up, but I'll fix this later on before I post everything here. But this is the next example. It's an in-class example, so it's real simple here. What we have here is we have a muon decays into other particles with a mean lifetime of 0.22 microseconds, as measured in a reference frame which is at rest. If muon travels at 0.99 relative to the Earth, what will be the observer on Earth measure its mean lifetime to be? Okay, so this 0.22 is the proper time. That's what the muon will tell you. My half-life is 0.22 microseconds. People on Earth say, you last longer than that. Okay, and so you got to figure out the gap. Okay, I think my daughter's okay. So if 0.22 microseconds is the proper time, we need to figure out the gamma factor for 0.99, which is, apparently, let's punch it in here, 1 minus point, come on, 1 minus 0.99 squared. Square root, flip the number. 7. My goodness. Gamma factor of 7. So 7 times 0.22, 15.6 microseconds. So people on Earth see the muon living a lot longer. Okay, great. All right, so I got one final question for you before we take our break here. All right, Samir, who is standing at rest on the ground, starts a stopwatch at the instant that Maria flies by in the spaceship. All right, Samir's S frame, Maria's S prime frame. Let's keep going. She continues to fly her spaceship at the same constant velocity according to Maria at the instant that Samir's stopwatch reads 16. Maria's stopwatch reads 20. Great. Okay, according to Samir at the instant that Maria's stopwatch reads 20, what does Samir's stopwatch read? All right, let me know what you think. Easier than you think. Easier than you think, but really good. A lot of D's and C's. And the answer is D. If you said C, you probably just did a little math thing wrong. But here's how it works here. We look at these two times, 16 and 20. Now guess what? Guess which one's the proper time? 16. Why? Because it's less. That's it. I mean, you could sit here and think about the events and all that stuff, but if you're presented two different time intervals for different observers, well, 16 shorter, right? So 16 is the proper time, and 20 is the longer time. So 20 over 16 is 1.25. So now if we go to, according to Samir, at the instant that Maria's stopwatch reads 20, Samir's stopwatch reads 20 is the proper time here. So we're going to multiply that by 1.25, and we get 25 seconds. Okay, so it's just this is a matter of saying, let's look at the numbers here. Saying, 16 and 20, 16 is the proper time because it's shorter. And then when we get to, according to Samir, the instant Maria's stopwatch reads this, his stopwatch reads what? Well, Maria is the proper time here. Samir has got a longer reading here. So with a gamma factor of 1.25, it's going to read 25. There's a very famous problem. In relativity that looks at some of the subtleties behind time dilation. And it's a very long and drawn out example that, to be honest, doesn't really establish much. It's a very interesting problem if you actually take general relativity. In special relativity, it's kind of not a very profound example, to be honest. And I think a lot of people don't really get the point of the paradox. So anyway, the idea here is this. We have twins, right? And the idea is and there's so many variations of this. I'm just taking the one from an old textbook I used to use. On the 25th birthday, Helen departs in the spaceship voyage to a distant star, right? And she's going to travel at 95% the speed of light. The spaceship is 9.5 light years from Earth. Okay. She arrives. She immediately turns around. She heads home at 0.95 C. Now, according to George, based on the distance to the star and the amount of time it takes. It should take 20 years, right? 20 years. And that's the 9.5 light years going there and back. It's basically 10 years there, 10 years back. So if you're, that's how long it would take. 10 years to go 9.5 light years at 9.5 the speed of light. So when she comes back, should be 45 years old. However, who has the proper time here? Helen has the proper time here. Okay, in Helen's reference frame, she's in a spaceship. The planet approaches her, and then it flies away. And then Earth approaches her. So, Helen is going to experience the proper time. Helen's clock is going to appear to run more slowly. The gamma factor for 0.95 is 3.2. So it takes 3.2 times less in Helen's reference frame. So when she gets back, she should be 31 years old, significantly younger than her twin brother. Okay, well, fine. Now, the paradox comes here. Let's see what Helen is going to observe. She's going to observe Earth flying away from her with George on it, coming to a stop, flying back to her, right? And so in her reference frame, it's George flying away, right? And kept flying back. So, and you flip things around, you would say, well, wait a minute here. If we let Helen be the, say, S frame and George is the S prime frame, you know, relative motion, right? Then the opposite should be true. George should be younger and Helen would be just fine. So you're into this paradox of like, well, who's correct? I mean, you can't have two situations where the other one is younger. And so you got to figure out which one's actually correct here. So what's the problem with this? The problem with this is that Helen's reference frame is not an inertial reference frame. It's not an inertial reference frame because what happens is as you travel there, you have to turn around. It means you have to come to a stop, speed back up. There's acceleration taking place. Now, it doesn't mean you can't solve this problem or anything. We don't have the tools to solve this problem because we're not dealing with accelerated frames of reference. You could do accelerated frames of reference. That's what general relativity is interested in. Or doing special relativity. In special relativity, we have to make sure that we have inertial reference frames. So the problem is that George's calculations are perfectly fine because he is in an inertial reference frame. Helen is not in an inertial reference frame, so the numbers that she works out are not correct. When you do incorporate the non-inertial reference frames in Helen's calculations, everything comes out just fine. So it's not really a paradox. It seems like a paradox, but there's an easier resolution to that paradox. And then generally what you would do at this point is say, okay, well, let's start looking at the math behind this. But we're not doing that. We're not looking at general relativity here. But this is perfectly fine. So if anything is to be learned from this is at the background of everything that we do, we have to be mindful of things are inertial reference frames. And, you know, for most of the examples that we will do, that will be the case. I'm not going to try to trick you or anything like that, although I would love to trick you, but I'm not going to be that evil. Okay, whoa. Okay, so now let's go back to that Saturn problem. Because there's something else going on there, to be honest. Something else is going on there. Let's revisit that problem. Okay, so you have this rocket that's going to travel from the sun to Saturn. And in the S frame, we see this rocket flying to the right at speed v. And if we relate that to distance and time, well, L would represent the distance between the sun and Saturn, and T represents the amount of time it takes for that journey. Okay, that's straightforward, right? Okay. In the S prime frame, though, the spaceship is stationary, and the sun appears to fly to the left, and Saturn as well. And so if Saturn eventually will catch up to the spaceship, and then we recorded another event here. And what happens there is the distance that travel is going to be different, right? And the rate at which time flows is going to be different, because the speed is not different. That's the thing, is that the speed is, this is relative velocity here. So the speed of the spacecraft and the speed at which Saturn is moving, they're the same. And so we actually did this ratio. I did an example of a person on a bicycle passing a lamppost and a street light. Right? No, it was a tree and a lamppost, right? And the velocity ratio is the same here, right? It's the same. So L prime, though, L prime is a different distance. That in order to make this ratio work, right, we know that the time flow is different. So the length has to be different in order for the velocity to be the same here. And this is what we call length contraction. And that distances are going to appear shorter when you observe things that are moving. That's the idea here, is that, so the person in the spaceship, they're in the S prime frame, and they say, I'm stationary and things are moving toward me. When we see things move, there is going to be a length contraction that takes place here. So now let's figure that out, because we know how to relate the times, right? So I'm switching over to the other notation here. So the S prime frame is the proper time, right? That's because the events are taking place at the same location. So the delta t that's here, we can change that into what it is for time dilation. We multiply the proper time by gamma, and that's the same as the time in the S frame. Well, the delta t's cancel out here, and now we have this relationship between the proper length, that is the length that is observed, in a frame in which the objects are at rest. That's divided by gamma. So remember, gamma is greater than 1, and so the contracted length is always going to be less. So there is another idea here of a proper length. We had a proper time, we have a proper length. And so what's really helpful when solving these problems or when thinking about them is to remember really clearly what the definitions of these things are. Proper length is how long something is when you observe them at rest. The person in the spacecraft is not observing the distance between the sun and Saturn being at rest. They're moving. Okay? The person that is on the Earth watching this take place has the sun and Saturn at rest relative to them. So the person on the Earth witnesses the proper time. Okay? So notice there's this difference where gamma lies. Here, the gamma is in the denominator. For time, the gamma was in the numerator. Okay? The moving reference frame experiences the proper time. Okay? The S frame is experiencing a proper length. When you reconcile those two things, that's what this relationship is right here, looking at these velocities. So that's an additional consideration to make, that when observing things that move, things are going to look like they are shorter. Okay, so. All right, now, that's a good example here. In particle accelerators, we accelerate objects to extremely fast speeds, and so the particles in those reference frames see a much shorter distance. In fact, in this example here, I just pulled this from an old textbook I used. this accelerator, it's a little up north from us, it's a 2-mile-long electron accelerator. But when you calculate the speed at which the electrons have been accelerated to, the length contraction goes from a mile down to 1 meter. Now, what does that do? Let me look up that, actually. So, that's a gamma factor of 3,220? What? That is wild. That is 0.999999036 the speed of light. That's crazy. That's crazy. But yeah, at that speed, lengths are contracted significantly. Cool. In fact, so what this means is, the implication of this is that objects that travel the speed of light experience a effectively infinite length contraction, which is true, actually. We do, like photons, for example. Photons don't necessarily travel distances because they are moving at the speed of light. Their length contraction is effectively infinite. So we'll get into that idea a little bit later in this class, actually. It's kind of interesting. All right, question for you related to length contraction. All right, so we got Samir, S frame, Maria, S prime frame. According to Maria, at the instant that Samir's stopwatch reads 8, Maria's stopwatch reads 10. You know what the proper time is now. According to Maria, her spaceship is 100 meters long. According to Samir, how long is the spaceship? Let me know what you think. Letter in the chat. And you can rule out 2 letters immediately, right? 2 letters you can rule out automatically. So 8 seconds is clearly the not good. Okay, let's talk about it. 8 seconds is clearly the proper time. 10 seconds is what the 8 seconds is the proper time. So the gamma factor is 1.25. Now Samir is watching an object move, right? And so what light contraction is light contraction is when you watch objects move, they appear shorter than they are. So the answer is not C, the answer is not D. It must be A or B. And if the gamma factor is 1.25, then 100 divided by 1.25 is 80. The answer must be B. Okay, so light contraction, at least conceptually speaking, is a little bit easier to comprehend because it's just a question of, are we watching an object move? If the answer is yes, then the length is contracted. The length never gets longer, right? The proper length is what it is when you're at rest relative to the ship. According to Maria, her spaceship is 100 meters. That is the proper length. 100 meters is the proper length because Maria is at rest relative to her spaceship. So that establishes the gamma factor, and then from there we take our 100 and divide by the gamma factor and we get an 80 out of that. Okay. All right. Any questions about that? Any questions? Are you sure if you don't have any questions? Everybody said D, and I want to make sure I'm clearing up any confusion here. Yeah, sure. Let's go through it one more time. Okay, Samir is the S frame. Maria is the S prime frame. She continues to fly her spaceship at the same constant velocity. She looks over and she sees Samir's stopwatch, 8 seconds. So what that means is that's the proper time because Samir says 0, and then Samir has 8 seconds, and somehow Maria can just see the stopwatch like really, really far away. But when she reads that, she's reading that according to what, she reads that, but it's not her event. That's why 8 seconds is the proper time. She's recording the events, right? When she records the events, 10 seconds elapse. but she can see that the stopwatch is shorter, therefore it's the proper time. All right, so that's 8 seconds is the events in Samir's reference frame he's at rest relative to his watch, right? Okay, so anyway, that establishes 8 seconds is the proper time. 10 divided by 8 is 1.25. That's the gamma factor. Okay, it's very easy to figure out how to do that, right? First of all, 8's the smaller number, so that's got to be the proper time. And then to get the gamma factor, it's got to be a number bigger than 1, right? So 10 divided by 8, that's where you get your 1.25. So Maria reports her spaceship is 100 meters long. So she is at rest relative to her spaceship. Therefore, she is reporting the proper length. Samir watches the spaceship move. Therefore, Samir is going to see a contraction. We take the gamma factor. 100 divided by the gamma factor comes up to 80. Okay, good. Good. Yeah, definitely, speak up if you got questions here, because here's the thing. Your normal response to this material should be, I'm totally lost. And if that's not, then that could be good. But this is not simple stuff, right? This is something that you have to sort of sit on for a while and ponder and do some homework and things like that, and before it really sort of sinks in. But this is weird stuff, right? It's weird because it's outside of our experience. These kind of speeds and to realize that length contraction and time dilation are sort of the norm. I mean, really, every time we did problems back in Physics 110, this was there. This was there. It's just that the gamma factors are so small that it's negligible. In fact, there's actually been a discussion, which I don't know, personally I don't think it's a good discussion, but and I've seen textbooks written this way, where you take a physics class and the first thing you learn is this. The first thing, before you do anything else, you learn relativity. And then, once you learn relativity, then you go into the other aspects of physics. And it's like, well, okay, I mean, once you've gone through physics, that context makes a ton of sense. I'm just not convinced that learning physics that's the way to learn physics. I don't know. I could be wrong about that, but I've seen it. Yeah, I've seen textbooks where they start with relativity. It's like, I don't know. It's like you tell somebody the world is really, 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 really complicated, and I'm going to tell you that right off the bat, and then we're going to make super simplifications for weeks and weeks and months, and then at some point we'll incorporate this complexity again. It's like, well, why did we even show you the complexity to begin with? Anyway, I rant. I'll stop ranting here. All right. So this is not a question to answer. We'll just talk about it. A miniature spaceship is flying past you. Okay. I don't know how small it is, but whatever. Moving horizontally at a substantial fraction of the speed of light at a certain instant, you observe that the nose and the tail of the spaceship exactly align with the two ends of a meter stick you hold in your hands. That's wild. Rank the following distances in order from longest to shortest. All right. The proper length of the meter stick, the proper length of the spaceship, the length of the meter stick measured in the spaceship's reference frame. All right. So, longest to shortest, all right? Let's try to reason this. Proper length of the meter stick. Well, guess what the proper length of a meter stick is? Somebody tell me what the proper length of a meter stick is. A meter. 1 meter, right? So that's 1 meter. So now we have to, so what's good to do is to try to figure if the other ones are longer or shorter. Proper length of the spaceship. Well, we're watching a spaceship move, are we not? Yes, we are. We're watching a spaceship move. That means its length is contracted. It's not a meter. It's longer. So automatically, B is greater than A. Automatically. Okay. Length of the meter stick measured in the spaceship's reference frame. Okay. Well, according to the spaceship's reference frame, the meter stick's moving. They're watching a meter stick move. So that means it's going to look shorter than it actually is. So it's less than a meter. That means it's going to be less than A. So that should be the ranking. A is a meter. B is longer than a meter. And C is shorter than a meter. That's a good question. I like that question. It's a good one. Any questions about that one? Is that unclear at all? Again, you're always asking yourself this question: are we watching a move an object? Right? If we're watching a move an object, the length is contracted. So we watch a spaceship move. It's shorter than it actually is. The spaceship watches a meter stick. Okay? So if it's watching a meter stick, it's shorter than it actually is. All right, great. Well, BAC, did I say that? Okay, good. I was like, all right, how are we doing on time here? How are we doing on time? Are we doing okay on time? Okay, right, let's get into problems now. Let's get into these problems here. Boy, everything is all mixed up here. I gotta really fix this. All right, spaceship flies past Earth. I'm sure that a spaceship flies past. Try that again. A spaceship flies past Earth at a speed of 0.99 c. Crew member on board the spaceship measures its length, obtaining a value of 400 meters. Ah, check that out. That's the proper length. 400 meters is the proper length because they're in the spaceship. They're at rest relative to the spaceship. 400 meters is the proper length. So 0.99 c, what is the gamma factor for that? 7.088. It's basically 7. So the length, according to the people on Earth, they see a much smaller spaceship. Kind of hard to see in the faded image here, but the spaceship is long, and then over here they look at it, and they're like, check out that spaceship. It is crazy small. It's only 56.4 meters. All right, so we divide our proper length by that. In this problem here, okay, you look at that 400 and you say, what length is that? Who sees that? That is proper length. Okay. In fact, let me bring up my other notes here so I make sure I'm on track. Oh, dinner's cooking. I'm getting hungry. My goodness. My goodness. All right. Observers in the figure below are 56.4 meters apart on Earth. Well, that's a weird number. That's the same number. How far apart does a spaceship crew measure them to be? The observers in the figure are 56.4 meters apart on Earth. That's the proper length. They're at rest relative to themselves, right? So that's the proper length. The spaceship, that means if you're in the spaceship, you're watching these two people fly past you. And so the length between them is going to be contracted. Okay? And so we divide that again by the gamma factor, we get 7.96 meters. Okay, which is crazy because what that means too is if you're in the spaceship and these people are flying by you, they're squished. They look like they're 7 times thinner than they actually are. They're going to look weird. They're going to look weird. Just take a picture of somebody, throw it in the MS Paint, and then take that image and just squish it down. What's factor 7? 14% down to 86% of its. Yeah. Anyway, so you get an idea of what the people in the spaceship see. It's little squished people. Well, they're not little; they're still tall. Right. The only affects the direction you're moving towards. So, all right, how are we doing here? Okay. Yes. So let's get back to the lecture here. We got how much stuff? 25 minutes. Good. Okay. So, do we have another problem here? Do we have another paradox? with our length contractions. Let's look at this thought experiment here, thought example. Carmen and Dan have meter sticks. Okay. They move 0.9 c relative to each other. Now, they both say, I got a meter stick. It's a meter long. Okay. And when Dan looks at Carmen, Dan does not see Carmen moving at, 1.8 c. It sees a different speed, which I'll tell you about on Wednesday. We're not doing that today. Oh, I'm not even doing the transformation equations today. Well, that's crazy. Wow, we have a lot to cover on Wednesday. Interesting. Okay, we have a lot to cover on Wednesday. All right. So, so what do they say? Well, I mean, they're both going to say, I see you moving. Your meter stick is way shorter than it's supposed to be. So Carmen's saying, Dan, your meter stick is really small. It's length contracted. And Dan says, okay, well, I see yours is length contracted. And so, Dan can't really say that, they're either shorter or they're longer, right? I mean, there has to be some resolution to this because they're both going to see this. And in fact, you think there'd be a paradox here, and there really isn't a paradox here. Everything's perfectly fine. Now, these are initial reference frames, so there's no trick there. Each one sees a shorter stick. That's it. And that's the resolution. There's really not a paradox here. The events that take place are, seeing a meter stick move past, a location or whatever. And, the fact that they both move means they both are going to see shorter sticks. There's nothing wrong with that. They'll disagree about that, but that's okay they disagree because they also disagree about other things like the rate at which time flows and things like that. But there's not a paradox here. They both do truly see different sticks. Now, there's actually another paradox problem that I kind of think I should prepare that one instead of this one here. But anyway, there's a thing about having a meter stick fly through like a shed. And the shed is not a meter long. Not a meter long. It's a really small shed or something. It's like an outhouse or I don't know. And what happens is people open and close doors of the shed, and in the thought experiment here, you can actually close both doors, and the meter stick can actually fit inside the shed, even though the shed is not even a meter long. And the resolution to that paradox is that the opening and closing of doors are not simultaneous events in different reference frames. That one makes your head hurt a little bit. I wish I could dig up that one. I think, does your book talk about that one? I don't know if your book does. Bar an example. But if it does, it's definitely a good read. That's definitely one of the more confusing thought examples, though, I think. Because it involves length contraction and time dilation. You have to think about both of those things to resolve that. Let me see if they got the bar an example in here. I don't think so. Nah. No, they don't. Alright. Anyway. I guess that's why I'm not including it, because it's not even in the book. Alright, so let's do another example, and then we wrap it up with some questions at the end. Okay, let's get into this now. Wait a minute. Oh, yeah, let's do the we're doing the Saturn example. All right, so in a previous example, we had the rocket traveled along a line from the Sun to Saturn at a constant speed. The Sun to Saturn distance is 1.43 times 10 to the 12 meters. What's the distance between the Sun and Saturn in the rocket's frame's reference? Okay, well, the 1.43 times 10 to the 12 is the proper length. The gamma factor for 0.9 is around 2.3. And so the distance between the Sun and Saturn is going to appear shorter. And you simply divide that distance by 2.3. We get shorter. So that's an additional thing that was happening. Not only is the events have a proper time to them, but the distance between these things are shorter. And in both cases, what you can do is this. You can say, okay, I'm going to take this distance right here and the proper time, divide them. You get a speed out of that. Well, guess what? That's going to be the same if you take the distance to Saturn, as seen from the Earth, and divide that by the amount of time it's observed to take place. And you get the same amount of time. So those two will match up in that sense. Okay, so let's go over some questions here. All right, so we're going to go and revisit that Peggy Ryan problem. We're going to revisit it today, and we're going to revisit it on Wednesday. I thought we were going to do our transformation equations today, but I guess I was mixed up in my slides. So Peggy passes Ryan at a velocity v. Okay, Peggy and Ryan both measure the time it takes the railroad car from one end to the other to pass Ryan. The time interval that Peggy measures is what the time interval from what Ryan measures. So this is a time dilation equation. You're trying to determine what the proper time is here. So what do you think is the proper time here? All right, so let's talk about, again, what is the definition of proper time? It's the length of time between two events that occur at the same location in their respective reference frames. What are the two events? The two events are this. The front of the car is at Ryan's location, right? So the front of the car passes Ryan, and the back of the car passes Ryan. In Peggy's reference frame, those are taking place at two different locations. At the front of the train and the back of the train. So if she has a coordinate system, they're taking place at different locations. What about Ryan's reference frame? At Ryan's reference frame, this is taking place at the same location. The front of the car is located at Ryan, and then it moves, and the back of the car is located at Ryan. So Ryan has the proper time here. Ryan has the proper time. Because again, according to the definition, two events that take place at the same location in their respective reference frames. In Peggy, they take place at two different locations. In Ryan, they take place at the same location, which is where he is standing. So the answer here is A. Okay, right? Answer here is A. Ryan measures the proper time because both events occur at the same position in his reference frame. I'm glad you guys got it wrong, because that means you're learning something. And every time you get something right, I figure, is this too easy? I don't know. All right, length. Peggy passes Ryan at a velocity v. Peggy and Ryan both measure the length of the railroad car from one end to the other. The length Peggy measures is what compared to the length that Ryan measures? I don't know. Every time I do this stuff, I'm like, Einstein was a freak, dude. What the heck, man? I hate to break it to everybody. It's not C. Okay, again, definition of proper length. The length of an object as measured when you are at rest relative to it. Peggy is moving with the railroad car. She's in the railroad car, right? She measures a length, that's the proper length. Ryan sees it move. If you see an object move, the length is contracted. So Peggy says it's longer than what Ryan says. There we go. It is A. So the key on both these questions is you got to really sit and think about observers. What are the reference frames? What are the events? And remember these definitions of proper length and proper time. Okay. So, all right. So, some of the calculations that we'll need to do to find relativistic corrections can contain numbers that are incredibly small. And as a result, a lot of calculators can't handle those calculations. For example, you can try in your calculator to figure out what gamma is for an object that goes 10 meters per second. If you try to put that in your calculator, you're going to get an answer of just one, exactly one. And clearly that's not the case. It's not one. It's just that the calculator cannot handle a number that's small. It's outside of how its variables are defined. So there's a way around that as an approximation. It's called the binomial approximation. And if you have a binomial, a 1 plus x to the n, if x is sufficiently small, much less than 1, then you can use a series expansion and take the first couple terms of that series to make an approximation of that. And the first couple terms in the binomial expansion is 1 plus n times x. So if we want to apply this to relativistic corrections, if we have the square root, so this will be 1 over gamma, the square root of 1 minus beta, where beta is velocity over speed of light, then that expression can be rewritten as 1 minus 1/2 v squared over c squared. If you have gamma itself, then it's a negative exponent, and so it'll be a plus in the first two terms of the expansion. So let's look at a couple examples of how this is applied, and so you can see how you can do this yourself. So in this example here, we have an airplane flying from San Francisco to New York at a steady speed of 300 meters per second. How much time does the trip take as measured by an observer on the ground, by an observer on the plane? So the ground frame, it's pretty straightforward. It's just a rate times time equals distance problem. The people on the ground are viewing the proper length for the trip, and the time they experience is just based on what they observe. So 4.8 times 10 to the 6 meters divided by 300 meters per second, 1.6 times 10 to the 4 seconds. Now the S prime frame is experienced in the proper time, because from their perspective, New York approaches them, and so San Francisco, New York events are taking place at the same location in their coordinate system. So to figure out the proper time, that's going to be the time that we just figured out, divided by gamma. Now, gamma is already a 1 over radical, so we can write that expression here as radical 1 minus 1 times 10 to the 6, that's the beta value squared, times 1.6 times 10 to the 4, that's the time in the ground frame. That radical can be simplified to 1 minus 1 times 10 to the minus 12. Now we want to apply our binomial approximation. We can rewrite that radical as 1 minus 1/2 times 10 to the minus 12 at the bottom here. And so what I'm gonna do is I'm just gonna distribute the 1.64 so we can see sort of what the value is and how it's adjusted. So if we factor that in here, we get the 1.6 times 10 to the 4, right? So that's the expected time. But the proper time is less by 8 times 10 to the minus 9. Now, that would be 8 nanoseconds. 8 nanoseconds, which is shorter by 1 part in a trillion. So it's for standard speeds that humans experience, these relativistic corrections are completely, so insignificant. One more example involving the length contraction. Let's do this one here. So we have an 8-meter long school bus that drives past at 30 meters per second. By how much is its length contracted? So 8 meters would be considered the proper length. Somebody in the school bus would see 8 meters. Somebody watching the bus drive by at 30 meters per second would see length contraction. Let's see, we want to determine what that is. So let's write out what that would be. So the proper length is 8 meters. we are going to divide that by our gamma value to try to figure out what the contracted length is. All right, so this is going to be 1 minus v squared over c squared. And then we could put our numbers in. If you plug your numbers in, the 30 divided by the speed of light, we're going to end up with a L naught radical 1 minus 1 times 10 to the minus 14. And that's going to be our length here. And so the binomial approximation is, again, 1 minus x square root can be approximated as 1 minus x over 2. All right, so let's rewrite that up over here. We're looking at now L naught 1 minus a half times 10 to the minus 14. So I'm going to put in my value for L naught here. That's going to give me 8 minus 4 times 10 to the minus 14. And that's what our contracted length is going to be. So it's 8 meters minus, and this value here is basically 40 femnometer, FM, femnometer, that's times 10 to the minus 15. So our school bus is 40 femnometers shorter. Now, what's a femnometer? Well, it's small. We're talking about something that is about 1,000 times smaller than the size of a hydrogen atom. So, how much does the bus contract by? Not even the width of an atom. Again, insanely insignificant for speeds that are very slow. But again, you start looking at gamma values when you start approaching a significant percentage of the speed of light, and it starts to become a big deal.